Hello everyone, I'm Vijay Lau from University Technology Malaysia. First of all, I would like to take this opportunity to thank Abadana Institute of Higher Education, Iran, for inviting me as keynote speaker for this conference. In this talk, I would like to present my research work on the synthesis of thin film composite membrane for potential recovery of saline water via greener approaches. This is the presentation outline for my talk today. First, I will give you an overview of the membrane technology and interfacial polymerization technique for the membrane fabrications, followed by progress of interfacial polymerization technique over the years. And then I will share or highlight our important findings based on the mixed-base IP process to synthesize the membrane for specific application. Lastly, I will conclude our findings. This is a membrane spectrum for water treatment. For those who are working in membrane research, I believe you are quite familiar with this spectrum. So we have microfiltration membranes as the most porous membrane, followed by ultrafiltration membrane, nanofiltration membrane, and lastly the most dense structure membrane, reverse osmosis membrane. In this research talk, I will focus mainly on nanofiltration membranes. So if you look at the spectrum, you will see that nanofiltration membrane is actually quite unique. It can remove small molecules from passing through the membrane while allowing small dissolved ion to pass through it. So typically, I would believe most of people, when they use a membrane, they would like to remove most of the impurity from the water so that they can produce a good quality of water, mainly from the consumptions, for instance. My research topic is about the recovery of saline water. So why we have to recover the saline water from the wastewater? Why is it so important? And here I give you two examples. The first is the textile industry. The industry use a lot of NaCl, which is between 40 to 80 grams per liter during dyeing process. So NaCl in this case is a compulsory during dyeing process to fix the dye onto a fabric. And when the dyeing process completed, the industry discharged a lot of wastewater containing NaCl and the dye. So in this case, we are thinking about, can we recover the saline water from this dyeing process by rejecting only the dye while allowing the NaCl to pass through the membrane. And when we are able to recover the saline water, this saline water can be reused again for the dyeing process, and you don't have to discharge it and use again the NaCl. And for the second industry, which is the oil and gas industry, and I believe most of you understand that in order to increase the percentage of recoverable oil from the reserve, the industry usually will inject seawater into the oil field, and this seawater, after completing the process, will be discharged together with a small amount of oil inside. And if you thinking about the saline water required, this is actually very important in this industry, because you can use a low pressure membrane to remove only the oil particles, but at the same time allow NaCl to pass through, and this NaCl, which is a seawater, can then be safely discharged into the sea. When we talk about the membrane for water treatment, particularly to remove small molecule from the wastewater, I think everyone must know that the only membrane can do so currently commercially is a thin film composite membrane made of the interfacial polymerization technique. So here I would like to give you a brief information about this technique. This technique was actually invented by Dr. P.W. Morgan in 1959. So at the time, the P.W. Morgan, he demonstrated that if you had two different monomer, immiscible monomer, and once they meet each other, they can start to crossing with each other at the room temperatures. So this process eventually adopted by a group of researchers from USA, and then they use this technique to form a thin layer on top of the microporous membrane, which is later commercialized for the nanofiltration and reverse osmosis process. So this diagram shows you how to prepare the polyamide thin film composite membrane using interfacial polymerization technique. First, you need to have a microporous substrate, and this substrate typically is actually an ultrafiltration membrane. Then you pour in the first aqueous solution containing a first monomer. After that, you contact this same membrane with the second monomer. Once these two immiscible monomers mix with each other, they start to cross-link to form a polyamide layer. And this layer actually is very thin, just several hundred nanometers. And what I want to show you here is between step 1 and step 2, the process, you need to use a rubber roller to completely remove the excess aqueous solution from the membrane substrate surface before you can introduce the second monomer. If you don't do that, you cannot produce a perfect polyamide layer. This diagram shows the development of the interfacial polymerization technique invented by different researchers worldwide since 2013 until 2020. So this finding has been published in our research and highly cited by researchers. So what I want to show you here is you can see that there are actually a lot of techniques developed by the researcher to address the issue faced by the conventional interfacial polymerization technique. And some of the techniques invented are support-free polyamide layer, which is this one. It means that researcher can fabricate polyamide layer without using the microporous substrate. Of course, this membrane comes with other issues like poor mechanical strength. And we have a researcher use dual layer slot coating. Instead of you pour the solution one by one, they will form the polyamide layer almost simultaneously using two solutions. Some use the ultrasound assisted IP, and our group actually previously we use vacuum filtration IP, and this technique we used before mainly to produce the graphene oxide incorporated thin film nanocomposite membrane. So we invented this vacuum filtration technique because we want to make sure there's no loss of the graphene oxide during the process, and the graphene oxide can be well deposited on the membrane substrate surface before polyamide layer formation. However, there's a limitation on this technique, mainly on the size of the membrane we can produce. Here I would like to present our key research finding based on mixed-bed interfacial polymerization technique in short form MIP technique. Configuration 1 and configuration 3 actually is the conventional IP process, where you pour the aqueous solution on the membrane surface, followed by aqueous solution removal using rubber roller. Then you introduce the second organic solution. Once the second monomer react with the first monomer, it forms the polyamide layer. For the MIP techniques, we instead of pouring the solution on the membrane's surface, we introduce the small droplets of the water on the membrane surface. This droplet typically has less than 20 micrometers in terms of the size. Because the size of the water droplets is very small, it actually gives very large superficial area, and this eventually lead to higher surface energy and make the process or the surface of membranes have a higher degree of wetting. So these are some of the key results we obtained from our experiment. CIP here means conventional IP process. MIP means the Mr. IP process. 1, 2, 3, 4 minutes here means the duration of the misting time. So if you look at here, the misting time actually is very important. If you miss the membrane too short, like 1 minute, you have a lot of a pinhole. This means that the membranes does not have sufficient monomer to form the polyamide layer. By increasing the missing times, you can see here the thickness of the polyamide layer increase. It means that you have a more monomer to react with each other, and thicker polyamide layer can be formed. However, we found that when you have too many monomer on the membrane surface through misting process, these small water droplets, they will form a larger water droplets on the membrane surface before you introduce a second monomer, and this actually cause a lot of the pinhole on the membrane surface, which is not good for the rejections. So what I want to highlight here actually is, if you look at this data, the MIP3, which is considered our best membrane, actually require less than 17 times chemical to form a polyamide layer. So we also do the EDX analysis for the mixed PIP 3 minutes membrane surface and the conventional membrane surface. So this yellow color actually indicate the monomer with respect to the nitrogen. So you can see here actually is we use 70 times less chemical to form the polyamide layer, but we still have more PIP, which is monomer, on the membrane surface compared to conventional techniques. So this is the TM image of the best MIP membrane 3 minutes, and this membrane have a 125 nanometer compared to the conventional membrane has 171 nanometers. So the advantages of this mixed-base IP technique is it can produce a free volume within this thin layer, and this can actually produce a membrane with higher flux. Using mixed IP technique, we further develop the thin film nanocomposite membrane incorporating graphene oxide with and without modifications. So this is a SCBN physical image of a different membrane. TFC membrane is a control membrane made of mixed IP, and when you have a graphene oxide within a thin film polyamide layer, then the thickness of the layer increase. But if the graphene oxide is modified by monomer, either AA or MMA, you will see that the layer becomes the thinner. This is because once you modify the graphene oxide, the exploration actually is better. Then this reduces the stacking effect of the graphene oxide. This is data of different membrane for the pure water flux and salt rejections. And for the control TFC membrane of the mixed IP techniques, the flux is about 9 mH per bar. And upon incorporation of graphene oxide, you will see that the flux further increase. This is due to the hydrophilicity enhancement on the membrane surface. When you use the hydrophilic monomer to modify membranes through the GO incorporation, you will see the flux can be further enhanced. However, if hydrophobic monomer is used for the graphene oxide membranes modification, the flux is going down. So you will see here that the best membrane performance actually is a TFM AAGO membrane. So this membrane, although it has a lower NaCl rejection, this will not affect its performance, because if you still remember in the early part of my presentation, we actually want to achieve high saline recovery rate. It means that we need the membrane to have a low NaCl rejection as much as possible. For the salt rejections, we actually don't really care about it, because the lowest is the better. For the dye filtration, you can see that most of the membranes are able to reject the dye perfectly, except for the methylene blue, because this pigment has the lowest molecular weight. We also tested the TFC and TFN AAGO membrane in the filtration process using fish solution containing NaCl and rotamine blue. Regardless of the NaCl concentration in the fish solutions, both membranes can achieve very similar rejection, which is close to 100%. For the NaCl rejection, you can see here that our developed TFM AAGO membrane actually has a lower NaCl rejection, which is good because we want to recover the NaCl from the solution. So because of this, when you look at data further, the TFM membrane can recover up to 86% of the NaCl from the fish solution, which is much better compared to the control membrane, while at the same time give you much better flux. And for the fifth SEM's TM analysis, you can see here that the stability of our membrane containing the graphene oxide before and after the filtration for up to 12 hours. And you can see here that graphene oxide actually is still embedded within the polyamide layer, and there's no reachings of the graphene oxide from the polyamide layers. In the conclusion, I would like to highlight that the MIST IP technique that was proposed here could actually produce the TFA membrane, but using much less chemicals to form the polyamide layer. In our case, we realized that it actually needs less than 17 times of the chemical to produce the polyamide layer. And using the MIST IP techniques, we also found that we can actually produce a membrane that has a potential to recover 70 to 89% of the NaCl from the feed solution, and by achieving a good quality of saline permeate containing less than 0.3% of the pigments. Lastly, I would like to acknowledge my former student Lotte Xia and Lotte Ku, who has assisted me for this research work, and my funder, Ministry of Higher Education and Ministry of the Science, Technology and Innovation. And this is the photo of my current student, a postdoc and undergraduate student. And if you are interested on what we are working on, we have a YouTube channel called More Than Practice. You can subscribe, and inside you can get a lot of information, not only about the membrane but also other separation process as well as the seminars. If you have any question, opinion or suggestion regarding my research work, you can always contact me via my email address here. And lastly, thank you very much for your attention.